the next session on ANSYS Workbench tutorials. In this session, we are going to analyze the water bottle for a thermal analysis. This time, we will analyze the bottle which contains hot water. We will start by double-clicking on Steady State Thermal module. We'll first go to Engineering Data and double-click. Engineering Data Sources, General Materials. We will choose 4 materials: aluminium alloy, copper alloy, stainless steel and polyethylene. Then we go to project and update project. Next we'll go to geometry and right click. Import geometry of the model. Then we'll go to model and double click. First we'll go to geometry and change the material of the bottle to say aluminium alloy. I'll change the material for both the cap and the body. I'll now go to mesh and generate the mesh with the default size. Next we'll go to steady state thermal. Here I'm going to right click and insert temperature on the outer surface. For the outer surface, I'll give the temperature as 25 degrees Celsius. Also, I will insert convection on the outer surface. Apply. Film coefficient I'll give as say 20 watt per meter square degree Celsius and ambient temperature is 25. Next I'm going to give temperature on the inner body. So I will first hide the cap and select the inner surface. I'll right click and insert temperature. This is containing hot water, so I'll give the temperature between 91 to 96 degrees Celsius. So let me give as 92. Now these are the boundary conditions. I'll go to solution and right click, insert thermal temperature. Also I'll insert thermal total heat flux and the directional heat flux. Then I'll go to solution and solve. First we'll go to the temperature. The temperature inside is 92 degrees Celsius and on the outer surface it is approximately 21.7, that is 22 degrees Celsius. If you click on animation, you can see the variation of temperature over the body. Then we go for total heat flux. You can see it is 3.186 into 10 raised to 6 watt per meter square maximum. Minimum is 149.21 watt per meter square. Now this is for aluminium alloy as the material. Then we'll go for directional heat flux along the x-axis. It is 2.423 into 10 raised to 6 watt per meter square. You can animate and check this result as well. So this value is obtained for aluminium alloy. Now we will change the material to say copper alloy. And we'll solve once again. Now I'm not changing the material of the cap, or I'm not making the cap visible, because with the cap you won't be able to see the temperature change inside the bottle. So now when you click on temperature, again you can see the temperature variation. The main important thing is the total heat flux, which is 8.25 into 10 raised to 6 watt per meter square maximum. Minimum is 1399.3 watt per meter square. And the directional heat flux along the x-axis, maximum is 6.24 into 10 raised to 6 and minimum is minus 6.227 into 10 raised to 6. So you can see here the average value is also given to the right. Here you can see minimum, maximum and average values. Now next we will change the material for the body to stainless steel, and we'll solve once again. The value of directional heat flux for copper was more than that of aluminum alloy. So now let's see with stainless steel what happens. First we'll go for the temperature. You can see the variation. We'll see the total heat flux, that is 3.1 into 10 raised to 5 watt per meter square, which means it is lesser than aluminum alloy as well. Then we'll go for directional heat flux, 2.35 into 10 raised to 5 watt per meter square is the maximum value. You can also animate and check this result. After this, we will change the material to plastic, that is polyethylene, and we'll solve once again. Let's go to temperature. You can see the variation. Total heat flux. You can see the maximum value is 5761.7 watt per meter square, which means very less amount of heat will be transferred because it is plastic. And for directional heat flux also you can see the value is quite less, 4359.4 watt per meter square. It's very less. The reason is because it's plastic, it is going to allow very less heat to be transferred. So with this I end the session. I hope you have understood the analysis. If you have any doubt, please write to me in the comment section. Don't forget to like, share and subscribe to the channel. Hit the bell icon for latest video updates. See you in the next session. Thank you.